Okay, our next step in learning how to do phasor analysis of sinusoidal AC circuits is to figure out how we're going to handle passive components. Voltage sources and current sources, we already see how to change sinusoidal values into phasor values doing a direct time domain to polar form transformation. But what about resistors, capacitors, and inductors? How are we going to treat those in the frequency domain when we start solving problems? Well, let's do a little analysis and let's see how we're going to make that work. So for resistors, let's first consider those. In the time domain, we know that V is equal to I times R. And of course, if V and I are functions of time, they change with respect to time, we could really say that V of t is equal to I of t times R, if you wanted to be more explicit about it. So let's put in some time domain equations. Let's let I of t be equal to Im times cosine omega t plus theta. So we can change this into polar form, where I would then be equal to Im at a phase angle of theta. So a direct time domain to polar form transformation. In that case, V of t will be equal to R times Im times cosine omega t plus theta. So just substituting this equation into Ohm's law. And that means I can convert the voltage into a phasor, which will have a magnitude of R times Im at a phase angle of theta. And so what we get here is Im theta is equal to I, and therefore this must be equal to I phasor times R. And so therefore V is equal to I times R for resistors. In other words, Ohm's law. Ohm's law holds in the time domain. It also holds in the frequency domain with phasor voltages and currents. We also note that V and I are in phase. In other words, they have the same phase angle. So when two phasors have the same phase angle, in this case theta, we say they're in phase. There's no phase shift. There's no difference in phase angles between the two of them. So this is true for resistors. So we see we're still working with Ohm's law. So that's resistors. What else? What about inductors? Let's look at those. And over here, I'm just going to write up here for resistors, V is equal to I times R. We'll keep that up here and come back to this later. But for now, let's look at inductors. All right, once again, in inductors, what's the time domain equation that relates V and I? Well, we know that. V is equal to L di dt, or, of course, V of t is equal to L di t dt. to be a little more formal about it. So here's our time domain equation. And once again, we're going to assume that the current is a sinusoid. Where I is equal to Im times cosine omega t plus theta. And once more, we can transform that into a phasor with a magnitude of Im and a phase angle of theta. So, let's consider what dI dt is equal to. What's the derivative of the current? Well, we're going to take the derivative of this sinusoid, and that will be equal to minus omega times Im times sine omega t plus theta. But we want to get that back into cosine form because we want to be able to compare our original form with this. What's the relationship of the cosine to the sine? Well, we recall once our trig identities that sine of x is equal to cosine x minus 90 degrees. So we can go from sine to cosine by subtracting 90 degrees. Therefore, this will be equal to minus omega times Im times cosine omega t plus theta minus 90 degrees. All right, so now let's take this and we're going to plug this derivative back up into here. And so what we're going to get then is that v of t is going to be equal to minus L times omega times Im times cosine omega t plus theta minus 90 degrees. So that is now our voltage expression with the derivative of it plugged in. And now let's take this and let's convert this into phasor form. In phasor form, this will be equal to minus omega times L times Im at a phase angle of theta minus 90 degrees. Okay, now we're going to do a little bit of math to this. We're going to use the property of polar form complex numbers to decompose this expression I just did. And I'm going to do it like so. I'm going to say that, and I should actually write that this is equal to V to be correct here. So V is equal to this expression. Let's rewrite this. So V is equal to, I'm going to say this is equal to omega times L times Im at a phase angle of theta multiplied times minus 1 at a phase angle of minus 90 degrees. So note, all I've done here is I've taken this expression and decomposed it into these two forms. So I factored out that minus 1 at a phase angle of minus 90 degrees. Let's evaluate this. This can be evaluated. So in this case, minus 1 at a phase angle of minus 90 degrees, I can add 180 degrees to that and multiply by negative 1. So this is just the same as 1 at a phase angle of 90 degrees. All right, so just added 180 degrees, changed the sign, and we wind up with this. What is this equal to? Well, 1 at a phase angle of 90 degrees is equal to cosine of 90 degrees plus j times sine of 90 degrees. Cosine of 90 degrees is equal to 0. Sine of 90 degrees is equal to 1, and therefore this is equal to j. So therefore, what we get is this. Therefore, the phasor voltage V is equal to J omega times L times the phasor current I. Actually, let me go ahead and put it this way. This is equal to J omega L times Im at a phase angle of theta degrees. So just plugging directly into that. And then this is clearly equal to I. And so I just substitute. And so this is equal to J omega L times I. So now look what I have is, in this case for the inductor, what I have is that L V is equal to I times J omega times L. All right? So, this is our expression for inductors. Now we note that between the voltage and the current, we had that 90 degrees phase shift, the difference in 90 degrees. We went from theta to theta minus 90. And so what we find is, for an inductor, this must be true. For an inductor, voltage leads current by 90 degrees. Or current lags voltage by 90 degrees. So we've got a 90-degree phase shift between voltage and current. And this is strictly due to the fact we take that derivative and we convert the cosine to a sine when we take the derivative. That introduces the 90 degrees phase shift when we switch it back to being a cosine again. So they're always going to be 90 degrees out of phase with respect to each other. So these terms, in phase and out of phase, you've probably heard words like that all your life. Well, it has specific meaning here. When two phasors are in phase, they have the same phase angle. When phasors have different phase angles, they're out of phase with respect to each other. And in this case, it's a 90-degree out of phase shift. Okay, that was inductors. What about capacitors? Well, after doing inductors, keep in mind, inductors and capacitors are duals of each other. So for capacitors, we have that I is equal to C to V dt. Or I of t is equal to C to Vt dt in the time domain. So given this, let's assume the voltage is a sinusoid. And therefore, we have V is equal to Vm at a phase angle of theta when we go to phasor form. Now, from this point, we can use exactly the same derivation we did for the inductor, except we're flipping voltage and current around, and we're writing this in terms of capacitance instead of inductance. But if we do that, we can show the following. So using the same derivation form as we did for the inductor, we can show this. I is equal to j omega c times V. So the phasor current's equal to j omega c times the phasor voltage. Or the phasor voltage is equal to 1 over j omega c times I. And so write this up here. I'll say that V is equal to I over j omega c. Okay. All right. Once again, we note there is a phase shift between voltage and current. And in a capacitor, in this case, current leads voltage by 90 degrees. Or voltage lags current. So once again, we have a 90 degrees phase shift, only in this case, the current leads the voltage instead of the voltage leading the current. All right, so here we have our phasor relationships for resistance, inductance, and capacitance. And note how I wrote these, and I wrote these this way for a particular reason. When we look at these, they all have the same form. They have V is equal to I times something. And in fact, we look at that and we realize all three of those equations have the form of Ohm's law. Okay? So this leads to this. Ohm's law, we can write that as V is equal to I times Z. All of these have that same form. The question is what is that Z term? Well, that leads to our next definition. Z is called impedance. We define Z is equal to V, phasor voltage V, divided by phasor current I for any passive circuit element. In other words, any resistor, inductor, or capacitor. And so from this, we can see that we can fit this definition in any one of those three elements. For a resistor, Z is clearly just equal to R. So the impedance is equal to the resistance, and we note that impedance has the same units as resistance, ohms. For an inductor, Z is equal to j omega times L. So J, the square root of -1 times radian frequency times the value of the inductance. And once again, that has units of ohms. For a capacitor, Z is equal to 1 over j omega c, or we can multiply top and bottom by negative j, and what we'll get is it's equal to minus j over omega c, and that way we're putting the j in the numerator. And again, that has units of ohms. All right? Now we note Z is a complex number. Obviously, it can be a complex number, but it's not a phasor. And this is something that people sometimes get confused about. Phasors are complex numbers, but not all complex numbers are phasors. A phasor represents the magnitude and phase angle of a sinusoid. But we're not talking about sinusoidal voltages and currents. We are talking about passive elements with particular values of resistance, inductance, and capacitance. So don't confuse these, but this is why you'll never see Z written with a bar over the top, because that would indicate it's a phasor, that you can turn this into something that looks like a sinusoid in the time domain. And no, you can't. Voltages are phasors, currents are phasors, impedance is not a phasor. So note, once again, how I wrote this. V phasor is equal to I phasor times Z. Now, along with this, with impedance, we can also define reactance. We define reactance as the imaginary portion, the imaginary portion of impedance. Reactance. And let me spell that just a little bit more clearly. Okay, so given this, I can basically expand upon this a little bit. Let me redraw this as a table here. Let's see, let's draw it this way. Here's Z, and so for resistance, Z is R, this is J omega L, this is minus J over omega C. So that's the impedance of each of those elements. Then we look at the reactance. What is the imaginary portion of R? R is a real number. You have zero reactance. There's no imaginary portion to a real number. What's the imaginary portion of this? It's equal to omega L. What's the imaginary portion of minus J over omega C? It's minus 1 over omega C. Okay? Now we note, once we start defining things using impedance, what this means is, given the definition of impedance, we can now apply Ohm's law to any passive element. We can now use Ohm's law. For any passive element in the frequency domain. So here is a real powerful use for this idea of impedance. It now lets us treat everything the same. All passive elements are now, we're going to be plugging them into Ohm's law as long as we're operating in the frequency domain and using phasors and complex numbers. Turns out that's going to be extremely useful to us, as we're going to see. Now, we can also go through, since we're applying Ohm's law and since we are defining impedances, we can also go through and consider how do impedances combine in series and parallel. Well, since impedance seems to follow the form of resistance, we can easily show the following. So we can show this is true, that an equivalent impedance in series must simply be equal to, if I'm combining impedances in series, it's just going to be equal to the sum of the impedances. So impedances in series combine just like resistors. We add them together. We can also show that impedances in parallel or have this form. Not surprisingly, it's 1 over Z1 plus 1 over Z2 plus 1 over Z3 all the way to 1 over Z sub n. So this looks exactly like the same form we had for resistors when we combine in series and parallel. And the nice thing about this is we could apply this to both capacitors and inductors. In the frequency domain, everything is the same. Nothing is flipped. So before, when we looked in the time domain and combined capacitors together, we had to use different formulas, the opposite formulas. But in the frequency domain, as impedances, everything combines exactly the same. So let's look at an example of that. What if you were given the following circuit? Given omega equal 5,000 radians per second. And this is important. You have to be told the value of omega. Given this value, let's say you were given this network. This is 100 ohms. This is 180 ohms. This is 96 millihenries. This is 1.667 microfarads. I want to find the equivalent impedance for this network of elements, given that this must be true. Omega is 5,000 radians per second. Okay? So let's transform this network of elements into the frequency domain. What happens to the resistors? Nothing. In the frequency domain, resistors remain resistors. 100 ohms, 180 ohms. The capacitor, we have minus J over omega C. Plug in omega equal 5,000, and what we will get is this is equal to minus J 120 ohms. Over here with the inductor, J omega L is our formula for impedance. Plug this in, and we're going to get J times 480 ohms. Now note something here you're going to see over and over again. The impedance of a capacitor is always negative. The impedance of an inductance is always positive. It's always going to be that way. If you get a positive impedance for an inductor or a negative impedance, positive impedance for a capacitor or a negative impedance for an inductor, look what you did wrong. You made a mistake. So let's take this now and let's combine this together. We're going to use the same rules of combining we did before. So what do we have here? These are going to combine into an impedance of 180 plus J 480 ohms when I combine those together. And now this is in parallel with this. And so what I've got is that my equivalent impedance is going to be equal to minus J 120 times 180 plus J 480 divided by 180 plus J 480 minus J 120. And that will be equal to 6 minus J 152 ohms. And now these elements, which were in parallel with each other, I'll wind up with those being in series with 100 ohms, and therefore this will be equal to, actually I should call this Z equivalent prime, which is just these elements here combined together, and then Z equivalent would therefore then be equal to 100 ohms plus Z equivalent prime, and that will be equal to 116, or pardon me, that should have been 16, not 6. So 16 minus J152, then it's equal to 116 minus J152 ohms. There we go. So all I did here was just go through and do exactly the same kind of element by element reduction we've done before. These combine in series, then this and this are in parallel, and once we compute that, we add that in series with this element. And here's our answer. So this is our value in rectangular form. We could also write the equivalent impedance in polar form. So in polar form, the equivalent will be equal to, in this case I can just take that, let's assume I plug it into a calculator, and what I'm going to get is equal to 191.2 at a phase angle of minus 52.7 ohms. So I could also write this in polar form as well. Now here's something I want to emphasize to everybody. Impedance is not a phasor. This represents in the time domain a resistor, a couple of resistors, an inductor, and a capacitor of specific values. That's what this represents in the time domain. I've seen many students in the past do things like this. I'll say, okay, convert this to the time domain. So instead of going back to a resistor, an inductor, or a capacitor, instead they'll do this. We'll say, well, Z of t must be equal to 191.2 times cosine 5,000 t minus 52.7 degrees ohms. I've seen many people over the years make that mistake. They treat it like a phasor. This makes no sense. There's no such thing as a sinusoidal impedance in the time domain. In the time domain, impedances return and turn back into passive elements. That's what they do. So in fact, what is this actual impedance look like? Well, it's got 116, so really when we think about it, I've got 116 ohms added to minus J152 ohms. And minus J152 ohms, since it's negative, it's got to be a capacitor. So really, this is what we have. This is really what this, when I combine those elements together in the time domain, I can reduce them down to a resistor and a capacitor. That is what this looks like in the time domain, not like a sinusoid. So watch out for that, because this is a common mistake. Just because you can represent this in a way that makes it look like a phasor. Impedance is not a phasor. And if you want to figure out what it's going to look like in the time domain, you have to put it in rectangular form and then look at the real part and the imaginary part and write down the two elements that would represent. All right? And of course, at this point, I could just take my minus J over omega C, plug in my omega value, and work backwards and figure out what actual capacitance value gives me this. Okay? Now, a few more definitions. Along with impedance, you remember before we had resistance, we had conductance, which was the inverse of resistance. Well, along that same idea, we can also define what we call admittance, which is the inverse of impedance. So Y, admittance, is just equal to 1 over Z. So it's basically the parallel of conductance versus resistance. And admittance has units of, once again, Siemens or mhos. If you are somebody who's been doing this for a long time, that used to be the nomenclature we used before. I've mentioned this before. And you can also see in a lot of papers admittance expressed as mhos in older papers. The imaginary portion of admittance is called susceptance. So just as reactance is the imaginary portion of impedance, susceptance is the imaginary portion of admittance. And if I wanted to make another table, I could easily do that. Once again, let's list my elements, RL and C. Admittance, what's the admittance of a resistor? G, the conductance. What's the susceptance? What is the imaginary portion of that? 0, because admittance is a real number. Pardon, not admittance, but conductance is a real number. L, in this case, it's 1 over j omega L, which is equal to minus j over omega L. And therefore, my susceptance is equal to minus 1 over omega L. For capacitance, admittance is equal to j omega C, and therefore the susceptance is equal to omega C. And so here we have our definition for impedance, which now lets us transform any element into the frequency domain. So now we can transform sources. We can now transform passive elements. But if we're going to jump in and start doing circuit analysis, we need to know one more thing. Ohm's law works. Do Kirchhoff's laws also work? Well, we'll look at that next time.